Hello, everyone, and welcome to BubbleRAN webinar. We are very happy to have you with us today for insightful discussion and learning session about MXAI and the Agentic Shift in network operations. My name is Greta. I'm marketing manager at BubbleRAN. And as you can see on this intro image, we have three speakers today. Andrea Leone, our AI engineer, Ilias Chachi-Stefanidis, PhD student at Eurocom and working with BubbleRAN, and Navid Nikaen, BubbleRAN CEO and professor at Eurocom. Before we start the presentation, I share with you some practical information. The chat is available for your questions, and our team is available to reply you, so don't hesitate to ask your questions. We will have a dedicated Q&A session in the end, and you can also keep some of your questions for this part, and then we can share them with everybody. This webinar will be recorded, and the recording will be available on our YouTube channel in the coming days. We kindly ask you to fill in a short questionnaire. It's very helpful for us as we build and propose these sessions to the telco R&D community. So please fill in few questions. It's very helpful for us, and the link is available in the chat. Then let's get started. I will give you a company presentation and a short product portfolio overview, and then we will look at today's agenda together. These three pillars on this image are the foundation of everything we do at BubbleRAN: automation, intelligence, and open ecosystem. You can also see the AI RAN Alliance logo on these slides. We are a member of AI RAN Alliance, which is dedicated to driving the enhancement of RAN performance and capability with AI together with industry and academia partners. At BubbleRAN, what we do breakthrough technologies in the area of 5G, 6G, O-RAN, and AI RAN. We accelerate innovation by making advanced telecom infrastructure and software accessible, flexible, and feature-rich. We enable building scalable, extendable, and customizable 5G, 6G ready networking solution featuring open AI RAN built on both open source and industrial grade software stacks. And we create an open ecosystem for 5G Open RAN, including a developer portal with toolkits, APIs, and documentation. Here, I let you discover BubbleRAN mission statement in a form of short video.
Our mission is to empower public and private mobile networks with fully managed, high-performance 5G, 6G software solutions that combine flexibility, customization, and scalability. Powered by pioneering applied research, we create breakthrough technologies that enable smarter and more efficient networks, transforming the future of connectivity.
And then BubbleRAN products. In our portfolio, we have 4 products: MX PDK, MX AI, MX Pro, and MX ORS. And all our products are compliant with 3GPP, O-RAN, and AI RAN. Today, we are going to focus on MX AI, our solution enabling acceleration of the development, deployment, and sharing of network applications across multi-vendor, multi-model, and multi-cloud networks. We published the pre-alpha version of MX AI in our latest software release, Crimson, in June this year. And for our customers, for the time being, we propose a free trial license of the MX AI solution. Now, let's detail together a little more our MX AI. So, MX AI platform, what it is? It is a multi-agent framework, including open O-RAN RAP software development kit and different agentic toolkits. MX AI Orchestrator can also deploy digital twins. And there is a connection to MX Hub, which is the registry for different kinds of artifacts for RAPs, XAPs, and AI agents. There is a connection to MX Data 2, which is the data lake, and the artifacts can collect and publish data from there. It's good to note that the artifacts can be both from BubbleRAN and other vendors, partners, and customers, as presented in this figure, vendor A and vendor B. MX AI also includes training materials. And for the software stack, MX AI is detailed in this figure, you can see. There is a user interface and human user on the top. Then you have MX AI Orchestrator, which takes care of planning, task delegation, and answer synthesis between the different task-specific agents that you can see just under. Telco APIs means we are aligned with Air1 and A1 interfaces. MX Orchestrator can also deploy digital twins to verify some actions proposed by domain-specific agents. And this simulation can be done in a safe environment. Then, what to do with MX AI? You can tame 5G 6G complexity by autonomously orchestrating multi-vendor, run and core with closed loops. You can make network operations proactive with AI agents detecting anomalies and predicting faults. You can reduce mean time to resolve from hours to minutes. You can run small language models fully on-premise or on edge. And you can share XApps, RApps, agents, and tuned models via MX Hub. And then let's talk about you. Maybe you're working in telecommunications, higher education, or research services. Maybe you are AI network engineer, AI researcher, or a professor focusing in AI and ML. Whether or not your title includes AI, you are warmly welcome to join us to this webinar, and you are interested in following technologies: intent-driven agent deployment, simplification of agent development, customization, and integration with BubbleRAN ToolKit, and run configuration optimization powered by multi-AI agents. You are perfectly in the right place today, because these are the exact topics we are exploring together today. Welcome again to this webinar, and now let's look at today's agenda on here. So we are going to talk about Agentic AI, about deployment, development, and optimization. We will start with introduction keynote by BubbleRAN CEO Navid Mikaen. Then the topic of Agentic AI deployment by Andrea Leone, our AI engineer. After, Andrea will continue about Agentic AI development with BubbleRAN ToolKit. And last topic is Agentic AI optimization, presented by Ilias Chachi-Stefanidis, PhD student at Eurocom and working with BubbleRAN. We will finish this session with a conclusion and dedicated time for your questions. Shall we get going? The floor is yours, Navid.
Thank you very much, Greta. So welcome everyone to this fifth edition of our Open RAN and AI mini-series. I just look at the first edition we did. The first edition was on 25th of May, 2023. So which is good. We already have 2 years of this continuous sharing the knowledge and insight with you. So here, since the title of this webinar is about Agentic Shift in network operations, I have prepared a couple of slides to kind of motivate you and explain why we are seeing this shift, what are the drivers, and where are the next big things in the agentic operations for 6G network. So in terms of agentic shift, what we see at the beginning is the 6G complexity. So we are seeing more and more dense deployment, more and more heterogeneous deployment, but also in terms of the vendor, the variability in the traffic and the applications, and also the mobility, and also the fusion of the physical and the virtual environment makes the single operator control breaks in the sense that it becomes too much complex for a single operators to operate the network. So towards this infrastructure, sharing is one of the way to cut the capex, but at the same time distribute the complexity of the network. Another step is the autonomy that we are moving from the manual network, which we saw in 4G systems, towards the more autonomous network empowered by cloud native deployment and agility. So this will essentially lower the OpEx, and one of the main bottlenecks in the OpEx is obviously the maintenance of the network. We also think we are moving from the single agent to the multi-agent. We see that one single big agent may not be enough in terms of being able to decompose the intent coming from the users, but also in terms of complexity and power consumptions. So it seems that having a more hierarchical multi-agent system is more efficient to be able to distribute the task and be able to efficiently solve the problem at hand. Another also a dimension is a symbiosis that which comes between the agent and the algorithms, between the human and the agents, and between the agent and the network. And one new concept that we are actually working is it is self-synthesized and evolving network. So this essentially allows the network to self-synthesize itself and delivers the connectivity based on the spatiotemporal traffic variability of the users and the network. And finally, we are having a very rich use cases, AR, VR, metaverse. This calls for synchronization and coordinations between the application, network, and agents across different stakeholders. So with all of this, we see that this agentic shift is something that is going to happen. So I'm going to walk you through one example to exemplify why we need a multi-agent system. So we have here human operators that are asking from the orchestrator agent execute a power management strategy to improve the average power consumptions of the RAN node in tracking area, let's say XYZ, over 24 hours weekday period by 10%. So we want to reduce the energy consumptions. Also aim for less than 5% degradations of the average throughput. So this could be one example of the intent from operators to an agent. So this, for instance, could be decomposed by this orchestrator agent into multiple tasks. For instance, it could be allocating less resources to XYZ tracking area, updating the network blueprint and the configuration file, or for instance, deploying XApp or RApp to reach the goal in a more continuous manner. So with this, we will see that this orchestrator agent that we see on the top here is going to receive the intent from the operator, understand this intention, and then decompose it to multiple agents. For instance, here, as an example, we are talking about SMO agent. If we talk about the ORAN terminology, non-arteritic agent, which by themselves, they're also going to use an API agent to talk with the underlying network. So this could be talking to the teleco API, whatever API the network is exposing, right? Whether it is ORAN or other type of API, like a custom API. But what we see here is that the intention is decomposed and delegated to different agents. Each agents, they coordinate with themselves, coordinate with the orchestrator, and then exercise the optimization and the operation on the underlying network. And again, as you saw before, so what we try to do with our MXAI is essentially to make this happen in a standardized way. You saw before that, so we have this concept of orchestrator agent, which essentially does the task delegation, answer synthesization, and also the planning, which dispatch the original intentions coming from the user through the user interface, through the UI, or through the API into diverse agents. It could be some of them. It could be the FCAP agents, which goes, for instance, for the fault management, configuration, or performance for security. It could go to the RIG agents in terms of applying a policy to the network for dynamic reconciliation of the policy and enforcement to the network. For the SMO, for probably for some observability, and so for this task may cause generation of the digital twin to validate hypotheses and see if some of the actions actually make sense to apply it in the physical network. MXAI also comes with a bunch of blueprints. Blueprints are nothing but recipes for different use cases for optimizing the network, for optimizing the operation of the network, for the network performance, and so forth. So these blueprints are also part of the MXAI. We also have agentic toolkits that Andrea and Elias, they're going to explain to you, which facilitates the development of the agents and plugging into this multi-agent environment. And finally, we also provide open ecosystem and benchmarking, so you can actually benchmark different agents and get some results and compare. Moving forward, we also see that the networks of the future will be also driven by artificial general intelligence like capabilities. So moving from automations to full autonomy. And in this region, we see that trustworthiness, explainability, and human interventions are quite crucial to make sure that whatever is done is traceable. We can actually observe all the actions and also audit them and validate them, and try to avoid, if there is any inconsistency in the actions, try to avoid in the future and learn from that. Again, with the same things, we also see this agent as a society of agents. As I said, we talked about multi-agent, but we are even pushing the concept to the society of AI agent that collaborates and reason together, because each of them, they have their own perspective. So for instance, in the example I gave you, some of them have the perspective of the SMO operations, and the other ones, they have the perspective of optimizations and the specific, RAN parameters, configuration, and so forth. So they are kind of collaborate and reason in order to continuously learn from the network and then synthesize the network to correspond to the actual requirement of the applications. There is this synergy between the applications and the network that we need to always bear in mind. So this actually calls for extreme and collaborations, negotiations, and also resource broking, which means that these agents, they need to negotiate with each other. If they have, let's say, some contradictory requirement, they need to collaborate, and they need to also ask for the resources, and they need to converge so that the network operates and moves forward. To this end, so the following of the sections in this webinar are as follows. So we are trying to cover the DevOps for agentic AI. So we are gonna first show you how to deploy a sample AI fabric. So you're gonna see what is AI fabric and how to deploy an AI fabric simply in the form of declarative intent-based deployment, and then develop your custom agent. So for instance, define the agent logic and then deploy it, and then how to optimize the network using symbiotic agents. So these symbiotic agents are the agents that are combining the large language models together with the algorithms to make sure that they converge fast, they are not hallucinating, and they deliver the expected results in due time. So these agents can use deterministic algorithms for higher trustworthiness. So with this, I will pass the presentation to Andrea, who is going to walk you through intent-driven agent deployment with AI Fabric.
Thank you, Navid. Hi, everyone. I'm Andrea, and I'm going to walk you through the next two demonstrations for this webinar. So the first one is going to be about intent-driven agent deployment with AI Fabric. And I would like to start by giving you the motivation for why we need the AI Fabric. As we are shifting from single agent to multi-agent systems, we see this additional complexity coming in the management of the life cycle of multi-agent architectures. And these architectures include the agents themselves, but also the LLMs that they rely on, and also like supporting services like MCP servers and databases. And this brings the need for a unified deployment unit for all of the aforementioned components, a scalable modular infrastructure to connect the agents in an isolated environment so that one unit does not interfere with the other units, and agent DevOps for continuous integration, deployment, monitoring, and optimization of our workflows. And the solution that BubbleRAN proposes to this problem is the AI Fabric, which is just the fundamental deployable unit for agentic workflows in general in MXAI. And the AI Fabric also enables a declarative intent-based deployment manner for these agentic workflows, taking care again of the three components that I already mentioned. So the AI agents, the LLMs, which can be hosted both on premises or in the cloud, and also the services. Here I mention MCP, which is the Model Context Protocol. Those familiar with the AI agents development already know this term most probably. It is just a standardized way to expose to the agents context or tools. Tools are just functions, code functions that can be called by the agents, but also databases and others. So this is a figure which shows how an AI fabric will look like once it is deployed. And I would like to put the attentions on two main aspects of this architecture. The first one is the multi-agent aspect. So here you can see we have three agents in this case, which are talking to each other using the A2A protocol, agent to agent. Again, this is a protocol which standardized the way in which two agentic applications communicate with each other. And the agents can also connect to external services which provide context or tools with MCP. But additionally, we can also expose the agents themselves as an MCP tool. So MCP can also be used for agent-to-agent communication, although we discourage this and we promote using the A2A protocol, but it can be useful for, especially for interoperability with external toolkits. The other aspect is the multi-LLM aspect. So you can see from this figure that different agents can utilize different LLMs to generate their responses. For example, here the blue agent is using an LLM on the cloud, as well as the orange agent, while the green one is using an LLM hosted on-prem on a GPU. And now this figure instead is showing a more practical example of what we are going to see also with hands-on in a couple of minutes from now. So you can see that we have a bunch of services, which are a front-end application for a UI to communicate with our agents. And here we have a vector database, which stores network configuration files. So we can imagine this AI fabric deployed on top of a network. And what we want to do is to monitor our network or to modify the network blueprint to deploy or remove some elements from the network. We are using one LLM, which is GPT 4.1 Mini. We will use this for this demonstration, but of course it's possible to also host, for example, GPT OSS or Llama or Nemotron or any other open source model on your GPU. And we will utilize two agents, an orchestrator agent, which given the user query will decompose the query into simpler tasks and will dispatch these tasks to a domain-specific agent. And then we will have an SMO agent, which instead is going to talk directly with the SMO. And it will utilize the observability database to monitor the network. So this is how I can deploy this AI fabric in an intent-based manner. You can see here I specify the services. I will assign a name to each service, and I will have to specify the image of the application that is going to be deployed. On this figure, you can see the colored part is what I am defining in this slide. Here instead, I'm defining the LLM. This is the part which is used to specify the GPT in the cloud. So GPT 4.1 mini is the model. We specify also the provider, an API key. Here I am not deploying it in the real example, but just to show you how you can specify a local model. It's very easy. You just need to specify the provider here and the name of the model again. And you have to provide a URL where the service which is hosting the LLM is accessible. And finally, for the agents, again, we need to specify a name for the agent in the deployment. The role, which can be either orchestrator or worker. Worker is for the domain-specific agents. Again, the container image for the application, the LLM, which the agent is going to use. And if the agent needs to access tools, you can specify this parameter here with all the services that are accessed. In this case, we only have the observability database. So I'm going to show you how I can deploy this on our testbed. So with this command, BRC is the BubbleRAN CLI tool, which I can use to deploy an AI fabric. From this UI, I will show you that at the moment, I don't have anything deployed. And once I run the command, here I have all the agents coming up. You can see the orchestrator, the SMO agent, and here we can also see which LLM they are utilizing and their role. Now I will run a command to port forward the UI to my laptop in order to access it from the browser. Here it is, and I can start talking with the agents. Okay, for example, I can ask if there is any network deployed. And as I showed you, now we don't have absolutely anything deployed. And so the answer is gonna be negative. I would like to stress that this is a live demonstration, so everything you're seeing is running in this exact moment. Here you see that we don't have any network element deployed, so we can ask to our agent to deploy a network for us. And now I'm doing this on purpose. I'm not providing any information about the network that I want to deploy because I want to show you how the agent is going to ask me at least for some minimal information to perform this deployment. So here it is asking for the name of the network, the name of the access networks to include, and if I want to include also a near real-time rig, flex rig, or not. So I will provide this information. For example, the network name should be let's say BubbleRAN. I want two access networks, let's say AN1 and AN2, and also include FlexRig. So yes, include FlexRig. I will send the prompt. And we get a successful response. So if I go back to the UI, you can see that the network is coming up. All the components are being deployed. You can see the AMF, FlexRig, GNode B. We have two GNode Bs since we asked for two access networks. And now, yeah, everything is running. So now let's use the agent also to delete our deployment. And here on the right, you can also see some metadata. You can see the token count, how many tokens the LLMs are utilizing, and also the total inference time. Okay, so now the network has been deleted. Very good. And we can also delete the AI fabric. So with BRC, delete AI fabric. I provide again the name of the AI fabric. And here it is. And we can also stop the port forwarding. So to wrap up, we've seen why we need the concept of AI fabric. So we need it as a unified deployment unit for multi-agent architectures. We have seen some key aspects of the AI fabric, in particular the multi-agent concept and the multi-LLM concept. We have seen how we can deploy an AI fabric in MXAI, which is BubbleRAN Agentic Framework. And finally, we've seen a demonstration with some agents coming from BubbleRAN Agents Inventory. And these agents are also available with the MXAI release. Okay, so we can move on to the next demonstration. This is going to be about developing and integrating agents utilizing our dev toolkit. So I would like to start by highlighting what the toolkit will take care of from the developer responsibilities, and what instead are the only developer responsibilities. So from this figure, you can see that the developer only needs to specify the logic of the agent. So this graph will represent the agent's logic. And then we have to specify also to define the LLM clients, which are basically HTTP clients which connect to an LLM, but they are coupled with a system prompt, a user prompt, and potentially a set of tools. So a set of functions that the agent can run to provide better answers. On the other hand, the SDK of the toolkit is going to expose our agents as a A2A or MCP server automatically, so you don't have to write any code for achieving this functionality. It also facilitates handling chat history. It collects metadata, as I also showed you from the UI a few minutes ago. And it also provides some pre-built workflows to facilitate the development. For example, the React workflow, which is a very common pattern. And finally, it facilitates response streaming because while the agent is executing this graph, we can get updates at each step to know where we reach, like which point we reached in the execution flow. So this is an example of pre-built workflows, which can be included in the higher level graph. So this is the React loop. React stands for reason and act, and it's a very common concept in agents development. So we can represent a React loop with just this simple loop between an LLM and one or more tools. So what is going to happen is that the LLM will think, it will call some tools, the tools will be executed, and the response is going to be fed back to the LLM. And at this point, the LLM can choose to provide a final answer, so exiting the loop, or perform another iteration. So call again some other tools to get more information. And yes, as I already said, this loop can be put inside one node of the higher level graph. As you can see here, we have three different layers of graph. The very higher level is this one, which we saw in the previous demonstration, because the agents can interconnect in a graph network. Then we have the agent's logic. So each single agent's logic is represented also as a graph in this way. And finally, we have these pre-built workflows, which are subgraphs, which can be plugged inside these blue nodes here for the higher level agent's logic. So now I'm going to show you an example of how we can develop very quickly a simple agent which is going to generate random numbers and provide some insights about some of these generated numbers. The first thing to do is to define an agent card. An agent card is basically this file here, something which looks exactly like this, which provides information to other agents about our agent's capabilities. So this is very important because other agents want to know what our agent is capable of doing before calling it. So here I'm just specifying that this agent is an expert in generating random numbers and presenting them in a nice format. After defining this, we just need to define the agent's logic in a graph. So first we need to define what is the state of our graph. In this case, the toolkit provides this agent state class in Python, which can be extended. And this class is going to force you to override two methods, which are very important. I'm going to explain what they do. So our state consists of only two strings, the query coming from the user and the response. And these two methods are used, the first one to convert the initial query from the user into the initial state for the graph. The second method is instead, it's used to convert each intermediate state and also the final state into a string for providing a response to the agent, to the user. And this string is available in this field of this structure, agent task result. Next, I define a tool. I want to use a tool to generate a list of random numbers. This tool is, as you can see, just a Python function which takes three parameters, how many numbers we want to generate and a minimum and maximum value for these numbers. We just provide this function to our LLM, and the LLM can decide to call the function to generate the numbers. And finally, the actual graph. So in the graph, first we initialize our LLM client. We will see this component at the end with the prompt, and we provide the tools to the LLM. Next, we define a React loop because, as I mentioned, I want the LLM to call the tool to generate random numbers. So this is a clear example of a React workflow where the LLM can call tools and then provide the response to the user. So you can see that I am instantiating a React loop and I am providing as a chat model client, the client that I instantiated one line above. And finally, I generate the graph. So I add one single node in this graph. This node is going to be just the React loop. So what I am doing is basically this thing here. I am creating this node. And now I will add one edge to go from the start node, which is going to be here to the React loop, and then one other node at the end. And this is where I do this. So I go from start to the generation node, which contains the loop, and then from the generation node to the end. And the workflow is finished. Finally, just one last thing, I will show you the LLM client. It's very simple. You just extend this class provided by our toolkit, and you provide a system prompt. You just pass this to the constructor of the superclass, and everything is going to be handled behind the scenes by our toolkit. So now let's say that we developed our agent. We want to deploy it on the cluster. How do we do this? We can just add this specification to the YAML file the same way that we saw before. So if we take the AI fabric that we deployed in the previous demonstration, now we are going to add this RNG agent here. So we are going to deploy the exact same system as before, plus this new agent. Of course, to do this, first I need to containerize the application. So I need to do a couple of extra steps, but then I can just specify the container image here in the YAML file and the agent will be deployed. So I'm going to deploy this new AI fabric right now. Again, with BRC install AI fabric 2. You can see here that all the agents again come up, but maybe you will notice that there is one additional agent, which is the RNG agent. Now, again, I need to port forward the UI. I will refresh the page. Let's see if this is working now. Okay, I think I need to wait just a little bit for the new AI fabric to actually be deployed. So it's going to fail a couple of times. Sorry, let me check if everything is running. Okay, yes, now we have everything running, so it should work fine. Yes, okay. And I will show you that we have exactly the same capabilities as before. So I can again ask if there is any network deployed. I will not go again through the whole process of deploying a new network. I will just show you that it's going to say, yeah, there is no network deployed at the moment because we deleted the network that we created before. But now I can also ask for new things. So I can ask, please generate 10 random numbers between, let's say, 23 and 57. And here we have our 10 random numbers. And as you can see, the agent is also going to provide us some interesting information about some of these numbers, which is what we asked for in the prompt. And again, I can stop the port forwarding and delete the AI fabric. So to wrap up this second demonstration, we have seen how the BubbleRAN RAP SDK facilitates agent development, integration, and reusability, because we can take one agent and utilize it inside different AI fabrics. We have seen how pre-built workflows can be integrated in your agent's logic as subgraphs. We have done a sample code base dive in to see some key features, very basic features of the SDK. But if you want to know more about it, I highly recommend that you go check our open documentation on the BubbleRAN website. And finally, we've seen custom agent integration and deployment using AI Fabric. So that wraps up my section. Thank you everyone for the attention. And now I will leave the floor to my colleague, Ilias.
So now we are going to study a real use case, and we are going to focus on RAN reconfiguration and how to optimize specific parameters of the RAN utilizing AI agents. So our use case is about uplink power control, and specifically we are going to talk a lot about the P0 nominal parameter. So what is P0 nominal? In the 5G NR, P0 nominal is the cell-configured nominal power offset used by the UE in the open-loop uplink power control formula. So in other words, it will affect how powerful is the signal, uplink signal from the UE to the base station. And here two parameters are important. So the physical uplink shared channel is the channel that shares the data. And here the P0 nominal PUSCH will determine the baseline uplink power of the UE. So it will follow this formula. So the P0, the power, will be the P0 nominal plus other PUE specific parameters. And there is also the equivalent for the control channel, the PUCCH, which is the same concept, but for acknowledgements and CSI reports. So why it matters? It matters because it is a real use case that we see it a lot in public networks and also in private networks. So it's very important because higher P0 nominal can give stronger signal and can improve the SNR and SINR and generally the reliability. But sometimes maybe we want to decrease a bit the P0 nominal to have less interference for the UE power and but this could also lead to higher errors. So it is a trade-off and it is highly studied. So these are some references from 3GPP here. You can take a look. So now let's give some examples to understand better the use case. So for example, you can have underpower uplink. The P0 is too low. So maybe you have two UEs in the cell. And if you have low underpowered uplink, you have missed acknowledgements, maybe uplink failures, and the coverage generally suffers. What we want is like an optimized uplink, a sweet spot. You have a stable error, you have reliable PUCCH and balanced interference across the cells. And the other end is the overpowered uplink, where the P0 is too high, and this causes, for example, interference between the neighbors, and it drains the UE battery, and you see marginal gains. You don't see real gains. So now we're going to see how we realize this in our architecture. So first, we start by building an open and AI RAN network. So as you can see here on the bottom, we have the core network 5G, 5G RAN, and UE. And we have the full 5G stack. Here we demonstrate with OAI, with Open Air Interface. On top, we build the ORAN architecture. We have our RIC and SMO, and all the interfaces R1, A1, O1, and O2. And this enables AI agents on top to use these APIs. So then we deploy use case specific AI fabric for this specific use case. And we have two agents here. We have the orchestrator agent, and we have the self-reconfiguration agent, as we call it. And it is modular for more agents to be plugged, as we discussed. So specifically, the self-reconfiguration agent will retrieve current KPIs and the P0 nominal value. It provides suggestions for optimizing the P0 nominal, and it can enforce a new P0 nominal. So the most important part is that the operator will give the desired intent, which is here on the top. So the intent will be to optimize, find the optimal, let's say P0 nominal, optimize the P0 nominal, to maximize the throughput, the SNR, and other KPIs. And here we are showing you that it is over-the-air transmission. It is a physical testbed. Here we built a Faraday cage. We have two USRPs, as you can see, and a UE. And inside the Faraday cage, you can see that these are the antennas of the UE and the antennas in blue of the USRPs. So this is over the air. It is important to say this. And let's see now how we build the AI fabric for the self-reconfiguration. So here we have the UI and the orchestrator I discussed. We use the GPT 4.1. And the self-reconfiguration agent uses two tools. So we use the KPI Mon tool in order to retrieve the downlink and uplink throughput live from the network and to observe the SNR and the current P0 nominal. And we have also the P0 enforce tool, which will enforce the new P0 nominal to the network. And based on these tools, the agent graph now can decide when to use the tools and what to recommend and to enforce the new P0 nominal value based on the intent. So now let's go to the terminal. So first I'm gonna deploy the network. And we can see here the network being deployed. We have one G-Node B. Here in the middle, we can see the network is called BubbleRAN. So now I'm going to deploy a monitoring ARAP in order to be able to collect the KPIs from the live network. So as you can see here in the middle, we have a monitoring Python dynamic XAP. This XAP is triggered dynamically by the ARAP, and it collects all the KPIs that we will need to access. And now I'm going to install the AI fabric. We call it P0 fabric for the P0 nominal use case. And here in this tab, we can see that the P0 fabric is installed, and it has the orchestrator agent, the P0 specialized cell reconfiguration agent, and the UI. So now let's check the logs of the base station. So we can see that the base station is up and running. So we need to connect our UE now. Let's wait a few seconds for the UE to be connected. Okay, so we see LCID 4, so the UE is connected. Let's test this with some traffic. Let's put 40 seconds of uplink traffic. Okay, so we see around 23 megabps of uplink throughput over the air. And now let's port forward the UI so we can access the agent. Okay, so we have access to the agent. The traffic is running, so now we can ask what is the current throughput SNR and P0 nominal of network ID BubbleRAN. So we see that the P0 nominal currently right now is -90, and these are the SNR. They saw a healthy SNR, and the uplink throughput that it saw, it was 3.5. So let me restart now the traffic, and I have prepared a prompt that we can ask for optimization here. I will copy the prompt. So we want to say, recommend a new P0 nominal value. Consider the current SNR P0 nominal and throughput of the network, and choose a single new P0 nominal in the range -70 to -120p. Pick a new one you think is optimal with the objective to improve the KPIs. So what we do is we give the optimization logic to the agent to provide us a recommendation on the fly. So let's check the throughput just finished. Let's see if the agent was able to capture it on time. So we see here that the agent orchestrator did a 4 steps plan, so a complicated plan to solve this intent. So it is recommended to lower the P0 nominal to -100. This is the proposal of the agent. So we could, and it gives also the rationale behind, potentially restore or improve throughput. We can see take advantages of this decision. So we can say, set the P0 nominal to -100 of network ID BubbleRAN. So we can ask the agent to enforce the new P0 nominal recommended by itself, by the agent. So confirm that applied, the agent response. So now, as we can see, the G0B has been redeployed. So we see that the logs are finished, and the cell has been reconfigured with a new P0 nominal. And we can send some traffic. Maybe we can try to disconnect and reconnect the UE. Okay, we see that the UE is connected. And now we can send the uplink throughput for 60 seconds. Okay, we see around 28 megabps, 26. So we have some improvements. We can come back to the agent, ask again what is the current P0 nominal and SNR network ID BubbleRAN. So, okay, it replied only for the P0 nominal. It depends on the context. Now we have a long context, but this is normal. So the updated P0 nominal is -100. And we can see that the throughput is continuing. So I would like to go back to the slides now. So the takeaway of this demonstration is to show that we can design a use case specific AI fabric. So this was for this particular use case. And we needed only these 2 tools here, the KPI Mon and the P0 Enforce. And we only touched the agent logic and the development of these tools. And immediately we had a full use case demonstration. So this gives us the possibility to build autonomous agents for network optimization. You can tailor it to your needs and designs and objectives. And we can connect with other agents from an open ecosystems, from other vendors or partners. And the idea is to build a more complex and AI fabric for more advanced use cases based on our needs. So the vision is that now that we have all the building blocks unlocked, we can identify our use case and our objectives, and we can build custom AI fabrics and scale it to larger networks. So for example, here we saw that we have MXPDK and MXDT. So we have a real physical network as we saw, and we can have also a digital twin for what-if analysis in real time. On top, we have the agent toolkits and RAP SDK. And then we can deploy different AI fabrics, connect them to each other. For example, here we have one AI fabric that is designed for SLA negotiations. So here maybe we have some stakeholders that they want to negotiate the SLAs of the network. There is a mediator that at the end of the negotiation will enforce the optimal SLA to the network. And in parallel, we can see that there is from the network side, from the operator side, or SMO, for example, we have the orchestrator that now will dispatch all the network tasks to other specialized agents. For example, maybe we have the digital twin agents to apply the what-if analysis scenarios. We have the SMO agent and RIC agent, and all of them, they are talking with an API agent. Maybe you have also other agents to help you, for example, documentation agents. And the important thing is the open ecosystem. So here, the agents, the RAPs and XAPs are developed and provided also by partners, and we create an open ecosystem to share the intelligence. So now I would like to give the floor to Navid Nikaim to show you the conclusions. Thank you from my side.
Thanks, Ilias. It was very interesting. Okay, so we reached the conclusion. So what we are observing is that the phase changes in the 6G ecosystem and economy that is driven by AI. We see a lot of changes in terms of how we are seeing the upcoming 6G network with the emergence also of the sensing into ecosystem of the 6G. We are seeing that the combination of this physical and the virtual environment driven by the AI is significantly changing the way upcoming 6G is perceived. So towards that, we touched base at the beginning about the new concept of self-synthesized network. This was also part of our talk in ITU a few months ago. So we are seeing that moving forward from multi-agent to a autonomous network and follow up to the self-synthesized network, we are seeing that the network needs the ability to compose itself and regenerate its capability to serve the users and the network. And this evolution happens over time and space. So depending on where the network is deployed, at which moment in time, there might be different requirement, different capabilities that needs to be augmented to support the users. So that is why we are coining the term self-synthesized network to say as a step after the autonomous network to bring the network that could actually regenerate itself and support the applications and the user requirement. So we see 4 pillars for these SSNs. One is obviously human-machine interface. We see metaverse to be quite instrumental to enable self-synthesized network. Open ecosystem in a sense that we might be having a lot of models, a lot of specific agents coming from different vendors or different providers that are got plugged into the network. So some of them are network centric, some of them are application centric, and some of them maybe are even infrastructure type of centric. So I remember discussing with a couple of other companies. They actually build an agent for the ORAN front haul. So that makes that this open ecosystems brings the ability of the network to, plug different tools and applications and the agents, and then and enhance and evolve the network capability. We also see as a third pillar collective intelligence. So we talked about society of agent, we talked about the multi-agent, and now we are talking about collective intelligence in a sense that the intelligence is distributed among many agents, and as a all, we create a more collective intelligence. And finally, the fourth pillar is the autonomous network services. And to conclude, actually, this multi-agent framework provided by MXAI, I want to really highlight here that we build all of our product and our technology based on three main pillars. One is automation, in the second one, intelligence, and the third one is open ecosystem. We see that network automation is fundamental to enable the agility in the network intelligence. We also saw that APIs, teleco APIs, whether it is ORAN or coming from the network management systems, are quite instrumental to exercise this network intelligence. I also need to mention that some of the intelligence might be built in the network. Some of the intelligence could be on the top. So you know that AI RAN is introducing AI for RAN, AI on RAN, and AI and RAN. So there are different type of intelligence that could be exercised on the network. So what we see is that a given network might have different optimization and operations to be let's say exercise. So maybe, for instance, for a given network, we might be having different AI fabrics that operates. One, for instance, operates on a P0 nominal to optimize the power. The other one could optimize on the mobility management, for instance. One AI fabric is specifically designed for the mobility management of the users, and another, for instance, AI fabric is designed for the resource allocation and the MAC scheduling, and for instance, for the RAN slicing. So after all, there are many AI fabrics running on the top of network. Each are collaborating internally, but also externally with each other to make the network more efficient and also more autonomous. As also we mentioned that the MXAI incorporates a user interface and API. It has a built-in multi-agent framework. It can talk with the generative network digital twin. So whenever there is hypothesis to evaluate, the agent automatically deploy a network digital twin to validate hypothesis and then recommend the actual actions back to the network using Teleco API. We also developed very nice blueprints. You saw the P0 nominal, but we are also working on some new blueprints, for instance, for mobility management. The toolkits that you saw Andrea explained is very powerful tool to help you quickly build your agent compliant with the A2A, MCP, and ORAN. So this is very important that you actually could get best of everything in order to develop your agent and plug it into live network, and also benchmark and benefit from existing agent that we developed. So you don't need to redevelop the SMO agent. You don't need to redevelop the digital twin agent. You don't need to redevelop the RIC agent and XApp. You can just develop a new agent and make use of this open ecosystem to build an AI fabric. So with this, I think this webinar is concluded. I pass the ball to Greta.
So let's move to the Q&A session. Thank you for all the presentations. So we have a lot of questions in the chat. Navid can pick up some questions and we can answer. We can take still some time for this and share a few questions with everybody. So feel free to put your questions whether in the chat or you can also open your mic and ask your question.
Yes. So we have some time, open floors for the participant to ask some live questions. Please go ahead. We're also looking into the chat. So we had one question that I see on the chat that is related to So the question is, by the time we make the decisions using the agent, the network status may change because RAN is very dynamic. So how we manage these decisions to be effective and on time, right? So one of the answers that we gave, well, all depends on the time scale. So some of the actions might be in the order of the real time or near real time, and some of the actions could be completely non-real time. So if you look at from the perspective of the RAP, they are non-real time, and the control loop is much larger. What we noticed is that with symbiotic agents that we design, we can get down to 50 milliseconds of the latency in terms of interaction with the underlying network. But not everything requires this low latency actions to the network. All right. Any other questions from the audience? Okay, so here, okay, one question is, what's BubbleRAN providing? So essentially what we are providing is the MXAI, is the agentic framework, multi-agent AI framework for building AI agents for the telecom, right? We also provide some pre-built agent. So this will help you to benchmark, for instance, the performance of different agents. If you want to compare, you can use the existing framework to build new agents, right? We are not really giving training. The training we give to share the knowledge with our community, right? We do have some trainings for our customers, but essentially here what we are providing is the teleco specific AI framework for developing new agents, new RApps that is compliant with the ORAN, compliant with 3GPP, and also compliant with the new agentic protocols A2A. So this is what we are providing. A lot of questions have been answered online. There is one question: how agentic system differentiate itself from SON? Okay, so self-organized network historically was vendor specific. So they try to self-heal, do the F-gaps, in a more automated manner, and using vendor specific protocols and APIs. Here at one level, we are trying to use a standardized API for the network, ORAN or network management system. But also another dimension is the context and the intelligence provided by the large language models and the agent, and also automation that is provided by the cloud native approach. So it probably at the end they reach the same objective, right? We don't have the proper results comparing the performance of the self-organized networking compared, for instance, to the agentic optimization and agentic operations. We don't have this comparison, but it's a good question. It's a good question. Yes, Nicola, please go ahead and ask your questions. You can open your micro if you want.
Okay, yes, thank you, Mikhail, for the very nice presentation of the demos. My question goes to, well, I have two questions. One more for the future. Are you planning to extend the intelligence, and more than the intelligence, the autonomy of the agents? So agents that are perceiving and acting based on prompts, but taking also more, let's say, initiatives on how to optimize control loops, etc. So one question is this one, and the other question is there any way in the current version of your MXAI product to talk that your orchestrator can talk with other orchestrators of other systems that are also agent based, and how you would do that.
Oh, the last one is a very great question. For the first one, so let me first understand the questions. How we can extend the intelligence, taking more initiative for the control loop
Towards autonomy.
autonomy,
Yes,
right?
towards,
So good.
yes.
So essentially, there are two things. We distinguish between, let's say, one, atomic operations. For atomic operations, for instance, hand over this user from cell A to cell B, right? This is the atomic operation. But then on the top, you have a logic that is actually optimizing over certain parameters. Maybe they're optimizing over energy, maybe they're optimizing over performance, right? So that logic, that control loop is constantly optimizing, getting the current performance. As Elias and Andrade showed, we have a specific agent with MCP that requests the observability for all the users. So based on the performance, you get the performance of the users. You understand their let's say rate. You also understand the cell, how many base stations are running, what are the energy consumptions, and this active loop will decide whether it needs to enforce a new policy or not. But the actual logic in, let's say, in the form of RAP. RAP could be developed in a form of logic. RAP could be developed in a form of agentic AI, right? So this RAP is constantly running. This control loop is running, but doesn't mean that constantly it's enforcing the control actions. It could, because in cloud native environment, we are considering idempotent action. So which means that you could constantly push the actions, the desired action. So the long answer short is that the logic is constantly running. There are some atomic operations that are realized in the form of XAP, for instance, run slicing, handover, or let's say beamforming. These are atomic operations, and that logic could optimize and enforce this optimization over and over, whether it is on a non-real time and or real time. This could be done, let's say, autonomously, because the RAP logic could be completely become autonomous using the agent. Did I answer your question, the first question?
Yes, thank you.
Okay. The question 5, the last question, is possibility to make the SMO agent to talk with another orchestrator from another domain. I think as long as there is a A2A protocol, I think the whole thing could be established, because I think we had use cases where the agents were outside of the AI fabric. For instance, this was the work we did with NVIDIA. We did work with them in a form of a blueprint that is essentially some of the agents were a specific NVIDIA agent. So this is possible, but be mindful about the logic. So that means that these two agents, they need to understand their own logic. I would say technically this is feasible. Semantically, the agents needs to understand each other. Now, if you tell me you have, for instance, two network deployed in two different clusters, and you have the same SMO agent in two cluster, they talk to each other, I would say this is highly possible. This is highly possible.
Yes, okay, thank you. Thanks a lot.
Thanks for the question. Any other questions from the audience? How much time do we have? We can take 2 more questions. Okay, there is one nice question. Does the coordinator decide which agent make the decision in a form of hierarchy? I would say this depends on the logic of the orchestrator agent, how to decompose the intent into actions, right? I don't know how this is in practice done. Do you guys know how the orchestrator agent actually decompose? Maybe you can explain.
Yes. So basically, we have only the orchestrator, which is deciding which agents are going to perform subtasks. But let's say like the logic of the orchestrator is the following. It receives the query from the user. It decomposes it in simpler tasks based on the agents that it sees available. And then it assigns tasks to each domain-specific agent. Maybe Greta, you can go back in the slides to the number, for example, number 14. Yeah, you can see from this slide. So there are these 4 domain-specific agents, which are the docs agent, SMO agent, non-real-time RIC, and API agent. And the orchestrator, based on the query, can decompose a complex task into multiple subtasks and call each one of these also in parallel. And also, this maybe also responds to Nico's question. So here you can see that also, for example, the SMO agent is able to call the API agent, as well as the non-real-time RIC agent. It is also able to call the API agent. So in this sense, we can also see the SMO and non-real-time RIC agents as a second-level orchestrator. But yes, we have this kind of a hierarchy in the system. I hope this answers the question.
Okay, so maybe the last questions, if any want to ask the last question of this webinar. So there is one question which says, can the intent be something else than a message, like a pattern of actions? So intent in general is a intention to do something, is the intention described by the user. But the question is, if could the intent encapsulate actions already? I don't know if I explained the question correctly.
I don't get it 100% what you mean with the pattern of action.
So
But
the question that is asked is, can an intent be something else than a message, like pattern of action? Or is
I would say yes. I would say yes. Like an intent can be very complex, it can be very simple, and if it is like a pattern of actions, maybe it is creating a chain of thought or a plan of actions, let's say. Or it can just be a declarative description of a very complex problem that then the orchestrator either will have to dispatch and create a very complicated plan to do. So it depends on the use case and on the objective of the operator. It can be.
this be the exact action to execute? Instead of orchestrator agent to infer, you directly give the actions, change the P0 nominal to this. The intention is actual action. This could be done, right?
Yes.
So that's the thing. So to answer your questions, Abdul Hakim, is that you can, instead of message, directly ask for an action to be executed directly. Like for instance, in the demo for P0 nominal, you can directly say, do this P0 nominal, enforce this P0 nominal to the network. Good. I think we are good with the questions so far. So I would like to ask all of you, we are having 60% in left for this webinar right now, to take few minutes to answer the questionnaires shared in the chat. This will help us to see what are the points you want to see for the upcoming webinars and what are the points we can improve. So your feedback is very much appreciated. With this in mind, I think we can close the webinar. And
yes. Thank you so much. We want to, on behalf of all entire BubbleRAN team, thank you so much for joining us today. And we hope you got some insightful and valuable takeaways and you enjoyed the discussion as much as we did. We will share the recording link with you as soon as it's available. And we will also share with you the slide set as you just saw. So thanks again. Thank you very much. Thank you. Bye-bye.
Bye-bye.